Okay, on the next slide, I'm going to list some steps for graphing polynomials. And the first step that we usually do is try to find the x-intercepts. Okay? So I want to remind you there's different ways of talking about that. The x-intercepts are the values when you take your function and you set it equal to 0 and solve, where the y value would be 0. Okay? So there's a lot of different ways to say that. Often we say we're finding a 0 of the function or of the polynomial in this case. Or that's another way of saying that that value, x equals c, is a solution or a root to the equation p of x equals 0. It also means that x minus c is a factor of the polynomial. That's often a tool of how we're going to find these things. We factor and set the pieces equal to 0 to find the solutions. So all of those things are equivalent. And that's going to be our first step on graphing polynomials. Now, sometimes you have polynomials that won't factor, and it's much harder to find the x-intercepts, and there's actually numerical ways to do that we've talked about. But we're going to look at some where we can factor and find the x-intercepts and go from there. So the general guidelines, and now these were written, I got these from the textbook that's assuming maybe you don't have a graphing calculator. So step 2 is a little bit different from what I think I would do with a graphing calculator, but your first step is to find the x-intercepts, and you want to plot those. Then, if you don't have a graphing calculator, you just have to make sure you plot enough points. So make test points, make tables with values that lie around the x-intercepts, okay, and make sure you have enough of them to try to see the picture. Now, usually what happens is with polynomials in the power, they start getting pretty large pretty quickly, and they usually don't fit in that negative 10 to 10 window in the y direction, and we'll have to change the window. And hopefully, if you're doing it by test points, you do enough points to see that. I'm going to show you how with our calculator we can find the max and mins, and then we'll know exactly how far we have to go in order to see the entire polynomial. You always want to make sure you can see the x-intercepts and all local max and mins on your graph. And then in behavior, we'll see it on our graphing calculator, but we can check in behavior to make sure we're seeing a complete picture. So plot the x-intercepts. If you don't have a graphing calculator, plot enough other points. If you do have a graphing calculator, plot the max and mins along with the x-intercepts. And using the end behavior, you can draw through the nice general shape for the graph. So let's look at an example. Let p of x be x to the fourth plus 7x to the third plus 10x squared. We're going to start by finding the zeros, which I would do whether the question asked me to or not if I had to graph it. That's what I would do first. But then part B, we're going to graph it. So the first thing we want to do, find those x-intercepts. Set our equation equal to 0, or set our function equal to 0. We get the equation 0 equals x to the fourth plus 7x to the third plus 10x squared. In general, a fourth degree equation could be very hard to solve, but we're lucky here. Every term has at least an x squared, and we can factor that out. So if we divide x to the fourth by x squared, we get x squared. If we divide 7x to the third by x squared, we're left with 7x. And if we divide 10x squared by x squared, we're just left with 10. So we can factor out x squared and get x squared times the quantity, x squared plus 7x plus 10. And then each of those pieces we set equal to 0, or I went ahead and factored it one more step. You could take your quadratic, x squared plus 7x plus 10, and set that equal to 0, which you could solve by the quadratic formula, but we can also factor it into x plus 2 times x plus 5. So if x squared equals 0, you take square roots, you get x equals 0. It's actually a double root. You get 0 twice from the plus or minus square root of 0, but you get 0. And then from x plus 2 equals 0, we get x equals negative 2, and x plus 5 equals 0 gives us x equals negative 5. So if we completely factor that, we find our x-intercepts are at 0, negative 2, and negative 5. And I can't remember, I know in the notes we talk about multiplicity. I think it's actually coming up in the notes, and we haven't talked about it yet, but when you factor a polynomial, the number of times that the root shows up is called the multiplicity. Negative 2 and negative 5 have multiplicity 1 because there's single factors that produce those. 0 is actually showing up twice. X squared is x times x. We're seeing 0 twice. When you have even multiplicity, you'll actually have a max or a min at that value, which is kind of an interesting thing to see on the graph. But anyway, we factored it out, and we got 3 x-intercepts, 0, negative 2, and negative 5. What I would then do is go to my calculator next. Okay? So we can hit y equals and type in our formula. I've got the screenshots here. I could do it live as well, but we've got the screenshots. We got x to the fourth plus 7x to the third plus 10x squared. I'm going to go ahead and look in the table and get some idea of what to do with my window. There's a couple of orders we could do this in. We could either plot it first and figure out a better window, or try to figure out a better window first. what we can do to figure out a good window to start with is go into the table, hit second and the graph button where it says table above it, and you can go into the table and look around the x-intercepts. Now it's going to go off to plus or minus infinity, and the numbers are going to get really large when you go beyond the x-intercepts. But I'm going to look between 0 and -5, and I see numbers like -32, -18, 4. So it looks like we don't have to go too high in the positive y direction, so 10 would probably be enough, but we need to go past -32 in the other direction. So let's see what I chose when I wrote the slides. I left my x's from -10 to 10 by 1s. That usually works unless you find x-intercepts out of that. So my y's, I did -40 to 20. Okay, -40 would be low enough to see a -32, and I went ahead and did 20. I could have done 10, but I did 20 for the y max. And I picked a scale of 5 if I'm going to go from -40 to 20. I could have done 10, but anyway, that's what I picked. And there's the picture the calculator gives me. Okay. If you do this in the standard window, you won't get a very good picture. Let me actually show you that with the emulator. So here's the SmartView emulator from Texas Instruments. So I can do y equals, put in x to the power of 4 plus 7x to the third plus 10x squared. And I'm going to hit zoom 6, which would be -10 to 10 in each direction. And if you drew this picture for me, I would not be very happy with it because you're not seeing a complete picture. You don't see the min. Okay? When you graph a polynomial, it's made out of these nice, smooth, continuous humps. You need to see the x-intercepts, and you need to see every max and min. So I can tell here it's going off the screen. It's a polynomial. It has to be continuous, dip down, and come back up. So we need a better window, and we could do trial and error. We could just go to the window and say, well, it's going down lower. Let's try -20. And of course, we'll see that's not low enough, and we could keep doing that. But as I showed you, if you do second trace, you can go into the table and actually look around at the values and look between the x-intercepts. They run from -5 to 0. So those are the values I got to worry about, -32, -18. So again, I decided that -40 would be a good y min. Wanted to go past -32, and I could set a scale of 5 or 10 or something and see that. And that picture would be fine. I did 20 a minute ago for that one. Let me show you an alternative way. Let's do zoom 6. I need to find the max and mins with my calculator anyway. I can find them even when they're not on the screen. We can do second trace and choose minimum here at number 3. And then remember, we need to give it a left and a right bound. You can move along the graph if you want. It will eventually come back up the other side. It goes off the screen. You can see the y values where it's dipped off the screen. Eventually it comes back up. Okay. That might be a little hard to do, though. You can actually use the x-intercepts. They make great left and right bounds. That min is somewhere between -5 and -2. So I'm going to set my left bound. I'm going to type -5 and enter, and it'll set the left bound at that x-intercept, and then I'm going to set my right bound at -2, the other x-intercept. So the max and mins, finding the max and mins, the x-intercepts make great left and right bounds for those, and then hit enter another time to get the guess. So we have a min, and it looks like the calculator got a little bit of round-off error. It's algebraically, I think it's exactly at -4, -32, but we've got approximately there -4, -32, and that's going to be important. We need that. And we can find the other max and min. You get a min at 0, 0. Remember I said that x equals 0 has multiplicity 2. You get a max or a min there. We actually have a min at 0, 0. That's also the y-intercept as well. You get 0, 0 as an x and a y-intercept. And we would want the coordinates of that max to draw a nice picture, so we can do second trace and choose number 4. And again, if you can see it on the screen, you might just want to use the arrows, but you could use the x-intercepts. I could do -2 as a left bound for that one and 0 as a right bound, and find that we have a maximum at -1.25 and then 4.4 if we rounded. Okay, and then we could fix our window and draw the picture. Okay, so let me return to my screenshots here. So I showed there I found the minimum and found the maximum. And then you have the one at 0. And then when you actually draw this picture, let's say you got to draw this thing on paper. So pick a good window that'll show it. I did -10 to 10 in the x direction, -40 to 20 in the y direction by 10s in the y direction. I always label just enough to tell what the scale is. If I'm going from -10 to 10, I can count the tick marks and see there by 1. And if I'm going up to 20 and I have 1, 2, 3, 4 tick marks, they have to be counting by 5s. and then plot your x-intercepts. We have 0, -2, -5. And then using my calculator where I found the max and mins plus looking at the picture, so we had a min at -4, -32. I approximate where that is, just past -30. And then we had the one at -1.25, 4.4 something, so I approximate that, and then we have 0, 0. So if you put in those 5 points, the 3 x-intercepts, which includes a min there, and then the max and the min, and you look at the picture and the end behavior, you can draw in a very nice graph of that polynomial. Okay? So that's my approach. Find the x-intercepts, graph it on your calculator, either pick a good window first by looking at the table or just experimenting, or go ahead and find the max and mins, or get a good window first and then find the max and mins. But to draw your picture, you want the x-intercepts, you want the max or mins, which we get with the calculator, and then draw a nice picture that shows all those. Always make sure you pick an appropriate scale to see all of the local max and local mins.